The moon. For more than half a century, every argument about the moon rested on the same assumption. We thought we knew it because we had pieces of it. Grey dust in lab trays, basalt shards sealed in plastic, numbers written in ink that said, "This is the moon." But all of those samples came from one side only, the face that always looks back at Earth. Then, in 2024, a capsule slammed into the grasslands of Inner Mongolia, carrying something no human had ever studied before: soil from the moon's far side. And the moment scientists began opening those far side samples, it became clear that the far side didn't match the moon in our textbooks. The chemistry whispered one story, the physics told another, and suddenly the moon we thought we knew no longer fit together the way it was supposed to. So what else have we been missing all this time? And if that question pulls at you even a little, good, because this is one of those stories that only gets stranger the deeper you go. So before we go there, take a second to like the video, subscribe to the channel, and let's unpack what China may have uncovered on the far side of the moon. The missing half of lunar history. When people hear dark side of the moon, they imagine permanent shadow. That image is wrong. The far side gets just as much sunlight as the near side. What it doesn't get is attention. From 1969 to 1972, Apollo astronauts landed near the lunar equator on wide, flat plains called Maria. Those dark regions were once filled by lava, which made them smooth enough for safe landings. Later, the Soviet lunar missions and China's Chang'e 5 followed the same logic. Different flags, same type of terrain. That created a blind spot. The far side is rougher, older, and packed with craters. It has fewer lava seas and a thicker crust. For decades, scientists debated why the two halves look so different, based on theory only, which raises an uncomfortable question. If half the moon was never directly tested, how many facts were really educated guesses? How China reached the unreachable. Landing on the moon is hard. Landing on the far side is worse. The moon itself blocks radio signals, meaning a spacecraft there cannot talk directly to Earth. That single issue kept the far side untouched for generations. China solved it with an idea first proposed during the Apollo era, but never used: a relay satellite parked near the Earth-Moon L2 point. In 2018, China launched Quick-Yao, a communications bridge hovering tens of thousands of kilometers beyond the moon. From there, it could see both Earth and the hidden hemisphere at the same time. That satellite made Chang'e 4 possible in 2019, the first soft landing on the far side. A rover named Yutu-2 rolled into the von Karman crater inside the vast South Pole Aitken basin, an impact scar nearly 2,500 kilometers wide and close to 4 billion years old. But Chang'e 4 only observed. It didn't return material. That final step arrived in 2024, when Chang'e 6 drilled into the far side and sent real samples home. And that's where the story truly starts. The first surprise: far side soil feels wrong. When scientists poured the Chang'e 6 samples into laboratory containers, the texture alone raised eyebrows. This wasn't the fine, fluffy powder Apollo crews described. The grains clumped, some particles stuck together, others formed irregular lumps instead of smooth dust. Under microscopes, mineral shapes looked unfamiliar. The composition didn't match near-side basalts or the Chang'e 5 samples collected from Oceanus Procellarum in 2020. Even before advanced analysis, one thing was obvious: the far side is not just cosmetically different. Its surface materials formed under different conditions. The location matters. Chang'e 6 landed inside the South Pole Aitken Basin, the largest confirmed impact crater in the solar system. The asteroid that carved it may have punched through the moon's crust and exposed deeper layers closer to the mantle. That possibility changes everything. If these samples include material from deeper inside the moon, then we're not just learning about surface dust, we're peeking into the moon's internal history. But what exactly does that history say? The second surprise: volcanoes that shouldn't exist. For years, the standard story went like this. The moon cooled quickly. Being smaller than Earth, it lost heat faster. The far side, with its thicker crust and fewer lava plains, should have gone geologically quiet early. The samples disagreed. Radiometric dating of basalt fragments from Chang'e 6 revealed volcanic activity around 2.8 billion years ago. That's shockingly late. Some Apollo samples are older than that. Even more startling, one piece of lava from the far side dates back roughly 4.2 billion years, making it among the oldest known lunar volcanic materials ever recovered. This creates a timeline that refuses to stay neat. The far side shows signs of both ancient eruptions and unexpectedly recent ones. That suggests the moon's interior stayed warm longer than models predicted, at least in certain regions. If the moon was still erupting billions of years after it was supposed to cool, what kept the heat alive? And what else might that lingering warmth have changed? The third surprise: a dry interior with a strange twist. Water on the moon has been a hot topic for years, especially after orbiters confirmed ice in permanently shadowed craters near the poles. But the Chang'e 6 samples told a different story. Analysis showed extremely low water content in the minerals, far lower than values measured in many near-side samples. This suggests the far-side mantle source was unusually dry. Not bone dry, but significantly depleted compared to the moon's Earth-facing half. That unevenness is puzzling. If the moon formed from the same debris cloud after a giant impact with Earth, why would one hemisphere hold more internal water than the other? Did something redistribute it early on? Or was the moon never chemically uniform to begin with? Instead of answering the water question, the far side samples sharpen it, and they hint that the moon's interior may be more lopsided than anyone expected. The fourth surprise: dust from before the planets. Among the most unexpected finds were microscopic remnants of Ci-like chondrite material. These are fragments linked to some of the oldest meteorites in the solar system, rich in volatile elements and primitive compounds. On Earth, such material is rare because erosion, tectonics, and water erase it. The moon, however, is an archive. No plate tectonics, no rain, no recycling. Impact debris can sit undisturbed for billions of years. The Chang'e 6 samples appear to preserve traces of ancient meteoritic matter that may resemble the material that bombarded the early Earth. This matters for a bigger reason. Ci chondrites are often discussed in theories about how Earth acquired water and organic ingredients. If the moon kept a cleaner record of those impacts, it might help scientists reconstruct events Earth itself forgot. Which leads to a strange thought. Could the moon, not Earth, be the best witness to how our planet became habitable? Half a story finally broken open. By the time researchers finished these first analyses, one conclusion was unavoidable. The moon we thought we understood was built from half the evidence. Chang'e 6 didn't reveal a single shocking object or hidden structure. It did something more disruptive. It showed that our assumptions were incomplete. The far side has its own volcanic rhythm, its own interior chemistry, and its own preserved record of the early solar system. None of this contradicts everything we knew. but it bends the story in uncomfortable ways. And this is only the beginning, because buried within those same samples is a discovery so unexpected that it forces scientists to rethink what nature itself can manufacture. If simple impacts and time can create materials we once believed required advanced technology, what else might be hiding in that grey dust, waiting for the next container to be opened? The final surprise that no one expected. Deep inside the Chang'e 6 samples, researchers found something that didn't fit the usual lunar categories of basalt, breccia, or regolith. Embedded within tiny grains were naturally formed single-walled carbon nanotubes, structures normally associated with clean rooms, lasers, and advanced manufacturing labs. Carbon nanotubes are cylinders made from rolled sheets of graphene. They are stronger than steel by weight, conduct electricity better than copper, and are used in high-end electronics, aerospace components, and energy storage research. Until recently, they were thought to require controlled industrial conditions to exist at all. Yet here they were, formed without factories, without humans, and without intention. Just vacuum, impacts, heat, and time. The moon had built nanotechnology on its own. That discovery alone forces a reset. If nature can assemble structures this complex under the right conditions, what other manufactured materials might already exist beyond Earth? How the moon built nanotech by accident. The formation process appears brutally simple. Micrometeorites slam into the lunar surface at tens of kilometers per second. The impact creates extreme heat and pressure for a fraction of a second. Iron-rich minerals act as catalysts. Carbon atoms rearrange. Under those conditions, carbon doesn't just burn away, it reorganizes. Sheets fold, tubes close. The result is nanoscale architecture assembled by violence and physics, not design. This isn't speculation. Laboratory analysis using transmission electron microscopy and Raman spectroscopy confirmed the structures. Their size, curvature, and bonding patterns match known nanotubes, except these formed naturally, likely billions of years ago. The moon didn't just preserve them, it created them, and that makes the lunar surface something new, not just a graveyard of impacts, but a slow chemical workshop operating for eons. Why this changes how scientists see the moon. For decades, the moon was described as geologically dead, cold, static, a leftover. Chang'e 6 disrupts that image. The far side samples show prolonged volcanic heat, uneven water distribution, preserved primordial debris, and now spontaneous formation of advanced carbon structures. These are not signs of a simple object. They point to a body with a long, uneven, and chemically active history. Even the moon's interior models are under pressure. Data from gravity mapping missions like NASA's Grail had already hinted at dense anomalies beneath the South Pole Aitken basin. Chang'e 6 landed in that exact region. While the samples don't solve that mystery yet, they strengthen the idea that the basin exposes deep lunar material never previously studied. Instead of answering one big question, the far side samples multiply smaller ones. And that's how real scientific revolutions usually begin. What China actually achieved. Strip away the headlines and speculation, and China's real achievement becomes clearer. It didn't find something secret, it removed a blindfold. Chang'e 6 completed the first full loop of lunar exploration. Orbit, land, drill, return from the moon's hidden hemisphere. That alone places it alongside Apollo in historical importance. But unlike Apollo, which confirmed expectations, Chang'e 6 disrupted them. This wasn't a lucky grab, it was the result of a methodical program. Chang'e 1 and 2 mapped the moon, Chang'e 3 tested landing, Chang'e 4 mastered far-side operations, Chang'e 5 proved sample return, and Chang'e 6 combined everything. Each mission reduced uncertainty until the final step became possible. What China really found wasn't a shocking object. It found evidence that the moon's story has been incomplete since 1972. The far side is no longer just harder to reach. It's scientifically richer than anyone assumed. It preserves older terrain, deeper material, and cleaner records of the early solar system. That makes it a priority location, not just for China, but for everyone. Future missions from NASA's Artemis program, ESA, India, and others are now being planned with this in mind. The moon's hidden hemisphere has gone from curiosity to cornerstone. There's also a practical layer. If the moon naturally forms strong carbon structures and contains usable materials locked in its soil, future exploration shifts from transport to extraction. Not tomorrow, not next year. But the direction is set. The moon is no longer just a destination, it's becoming a laboratory, and possibly one day an industrial site shaped by physics rather than factories. The bigger question no one can ignore. Every major moon theory, from the giant impact hypothesis to thermal evolution models, was built using near-side evidence. Chang'e 6 proves that approach was incomplete. If the two hemispheres evolved differently, cooled differently, and stored different materials, then the moon is not a single simple outcome of one event. It's a record of processes unfolding unevenly over billions of years. And that raises a deeper question. If our closest celestial neighbour fooled us for half a century simply by hiding one side, how confident should we be about objects we've never sampled at all? Mars, asteroids, moons of Jupiter. The lesson cuts far beyond the moon. When people ask what China really found on the moon, they often expect a single answer, a thing, an object, a reveal. But the truth is quieter and more unsettling. China found that the moon we thought we understood was based on half the evidence. The far side didn't contradict the past, it exposed its limits. With one capsule of grey dust, decades of certainty softened into questions again. And that's not failure, that's progress. Because the moon hasn't changed, we have. And for the first time since humans left footprints in lunar soil, we're finally starting to read the whole story, not just the side that was facing us.